All right, in this video, I'm going to cover section 2.2, fixed point iteration. So, so last time in section 2.1, we learned about the bisection method, which is one of the basic methods for solving root-finding problems. So now we're gonna mm, modify the root-finding problem to fixed point problem. So look at this. What's a fixed point? A number p is a fixed point for a given function g if g of p equals p. So the for given function g, if g of p equals p, then the p is called the fixed point. So now then, if function g has a fixed point p, then the function defined by f of x is equal to x minus g of x has 0 at p. So now then, since if p is a fixed point of function g, then a function defined by x minus g of x has 0 at p. Does it make sense, right? Because f of p minus g of p equals 0, because p minus g of p is 0. So now you see that here the goal is to modify the root finding problem, the function in the root finding problem f of x equals 0. We're gonna modify the function f of x to x minus g of x. Okay, so now then the we root find problem will be transformed to the problem g of x equals x, right? So although the problems we wish to solve on in the we wish to solve are the in the root find form, the fixed point form is easier to analyze, and certain fixed point choices lead to a very powerful root finding technique. So now his question then, does a function have a fixed point, and how the fixed points can be approximated to within a specific accuracy? So here's 2.2. So if g is continuous function on closed interval a comma b, and the y is defined by g of x, then g of x is belong to closed interval a comma b. It means that the range of function g of x is also is equal to domain, the closed interval a comma b. Okay. So now then G has a fixed point in the closing of a comma b. So uh, so simply saying that I mean theorem 2.2 means that if function is continuous on closing of a comma b, and then its range is also closing of a comma b, then function G has a fixed point. It means that there exists p such that G of p equals p. So now the second statement of theorem 2.2, if there exists derivative of g on an open interval a comma b, and then there exists the positive constant k less than 1, it means the k is between 0 and 1, with the the maximum, the absolute value of maximum of the derivative of g is bounded by k. Okay, and the k is between 0 and 1. Okay, for any x, then there exists uniquely. The exclamation mark means unique. Okay, so there exists uniquely exists the fixed point in the closing number a comma b. So we'll see the proof. So now let's see. Okay, so a, if here, see that the we wanna prove the existence of g. Okay, so statement a in theorem 2.2 is talking about uh, the existence of fixed point. Okay, and then b is talking about uniqueness of the fixed point. Okay, so now to prove the existence of function g, okay, so we're gonna start from this: g of a equals a or g of b equals b. Then g has a fixed point at an end point. If not, you see that? Not, then g of a is greater than a, and g of b is less than b. Okay, then let me see. Give me a second. Then what? So normally here we because if g of a equals a or g of b equals b is trivial, right? So a is a fixed point or b is a fixed point, right? So we don't consider that case, but we're gonna case this one. G of a is greater than a and g of b is less than b. Okay. So now function h of x equals g of x minus x is continuous. So now we define a function h. We define function h as g of x minus x. Okay. Therefore, this is continuous. Why? Because the problem says theorem A, the assumption is this g of function g is continuous and closing of AB, right? So g of x is continuous function, and then minus x, x is a polynomial. Polynomial is continuous on the set of the real number, right? So g of x minus x is continuous definitely, and then h of a. See, we assume the g of a is greater than a, and the g of b is less than b. Okay, so the g of a minus a must be what, greater than 0, because g of a is greater than a. The h of b is less than 0. Now we then use the intermediate theorems. So h is continuous, and the h of b is greater than 0, h of b is less than 0, then there exists what? The x coordinate of x-intercept of function h, right? There exists p such that h of p equals 0. We use that intermediate theorem to build up the bisection method in section 2.1, right? So now then, so HP equals 0. HP equals 0 means that GOP minus P equals 0. It means that GOP is equal to P. So P must be a fixed point, right? So proof done. So now suppose that, to prove the statement A, theorem 2.2, we use intermediate, we define h of x as h of x minus x, and then we use intermediate theorems. Okay, keep in mind this. And then B, suppose that P and Q are fixed point enclosed in a comma B, and the P is not equal to Q. So now let's see. The B's statement B is talking about what? Uniqueness. To prove the uniqueness, we suppose that there exists two fixed point, and then we can show that that causes contradiction. Okay, that's a way to prove the uniqueness. So B, suppose P and Q are fixed point in a closed interval A comma B, and the P is not equal to Q. And then so there are two distinct fixed points, right? And then we're going to use mean value theorems. Mean value theorem is what? There exists what? The x value such that the derivative of function x, that x value is equal to what? The the slope of the secant line passing through the endpoint of the graph, right? So mean value theorem implies that there exists cosine p and between p and q such that g of p minus g of q over p minus q is equal to g prime of cosine. So we can see that, right? So since the what function g is continuous, that's the assumption, right? And then let me see. So then g of p is not equal. So p and q are fixed point, but they are distinct. So g of p and g of q are different, right? Okay. So then the we can figure out the slope, the secant line passes through p comma g of p and then q comma g of q. And then by the mean value theorem, there exists x value between p and q such that derivative of a function g at psi is equal to the slope of that secant line. Okay, so with this, thus the p absolute of p minus q is equal to. So you see that here, this one, the left hand side represent the slope of secant line, right hand side is represent derivative of, I mean, slope of tangent line at cosine. So now we're gonna multiply by p of q, p minus q, the denominator on both sides, and take absolute value. Okay, so now see that. Now then we got this p absolute p minus q is equal to the absolute value of g of p minus g of q, because p and q are fixed point. So we can say that p is equal to g of p, and then q is equal to g of q. Now this guy is equal to what? By that formula, we multiply by p minus q on both sides, and take absolute value, you're gonna get this. Okay. So now that is less than or equals to k times p absolute value of p minus q. Why? Because the in the statement B says that what? Statement B says that the absolute value of g prime is bounded by k, and the k is between 0 and 1. So because of that assumption, the absolute value of g prime cosine must be less than or equals k. Sorry, it should be absolute value. There it should be absolute value right there. It's a typo. So it should be absolute value right here. Okay. So now then, since this guy is less than or equals k, so we got this, and then k is between 0 and 1, less than 1. Less than 1 times absolute value of k, p minus q must be less than 1 times p minus q. So we got this p minus q, absolute p minus q is less than, right? Less than 1 times p minus q. That doesn't make sense. Contradiction. Why we got contradiction? Because what? We assume that we suppose that P and there exists two distinct fixed point. Because of that supposition, we got this contradiction. So it means that P and Q must be equal. Okay. So you just see example 2. So I know, so okay, we proved the theorem 2.2, but it's a little bit, abstract. Um, we feel like it's too much abstract about the concept. I mean the concept of the fixed point iteration, method. So see example 2. Okay, so let g of x is defined by x squared minus 1 over 3 on closed interval negative 1 to 1. The check if g of x satisfies the hypothesis of theorem 2.2. So the we're gonna first in the example 2, we wanna check if g of x satisfy hypothesis of theorem 2.2 so that we can guarantee that this function g of x has unique fixed point. Okay, and then we're gonna study the algorithm of a fixed point iteration method. So first one, function g is belong to as is continuous function closed in negative 1 to 1. Yes, because this is the what a polynomial function. It should be continuous on everywhere. Now then, the range of g of x. To figure out range of g of x, we have to find the absolute maximum minimum. Okay, so then we have to find the critical values. So figure out the relative maximum minimum, and then evaluate the function g at endpoint negative 1 and 1, and then figure out the maximum minimum out of them. So the absolute maximum of g occur at x equals 0. I mean, so this function has a relative maximum minimum on negative 1 and 1. Yeah, so you can figure out, okay. So now let's see. Let me see right here. A second. Yeah, so I'm sure that 0, let me see. Yeah, I think 0 is critical value. So g of 0 equals negative 1/3. That's the relative, um, well, relative minimum. Okay. So and then we're gonna evaluate function g at the end point negative 1 and 1. So but g of plus 1 and g of negative 1 turns out to be 0. Okay, so then negative 1/3, negative 1/3 must be absolute minimum. So absolute minimum occurred at what, x equals 0, which is negative 1/3, and absolute maximum occurred at 0, a negative plus and plus minus 1, and which is 0. So okay, so now then so absolute maximum 0, absolute minimum negative 1/3, they are within the closed interval negative 1 and 1 comma 1. So we can say the range is belong to the domain closed interval negative 1 and 1. Now, so from the first from the first and second the description, we can say that okay, function g has a fixed point. So how many? From first and second, we proved the existence of fixed point of function g. Now we have to show the uniqueness of function g, fixed point. Then we need to figure out the whether or not the absolute value of g prime is bounded by k, which is between 0 and 1. Okay, so g prime is 2x over 3. It makes sense, right? And then since this is a linear function, right? So on closed interval negative 1 and on the interval negative 1 and 1, the maximum value of 2x minus 3 going to be 2/3, right? So because this is a linear function. So absolute value of 2x over 3 is bounded by what? 2/3. Okay. So G satisfies the hypothesis of 2.2 and has a unique fixed point. We proved that. Okay. Now, then the fixed point of g of x can be determined algebraically. Yeah, so let's figure out then, let's find a fixed point. So p equals g of p, we solve it. Okay, but g of p is what? P squared minus 1 over 3. So we gonna solve the algebraic equation p equals p squared minus 1 over 3, which is p squared minus 3p minus 1 equals 0. Because we just multiply by 3 on both sides and then get 0 on the right hand side. Now then, so yeah, this is a quadratic equation. We can solve it, right? Solving using quadratic formula, we're gonna get this half times 3 minus square root of 13. So is that you have to check that that p is on the closing number negative 1 comma 1. Okay, so that yeah, so look, I mean, yeah, so then yeah, so this turns out that this is in on the negative 1 comma 1. Uh, oh, sorry, not negative 1 comma 1, sorry. So, but it's, I mean, 3 minus square root of 3, 13. 13 is on negative 1 comma 1. But you see that 1 half times 3 plus square root of 13 is not on negative 1 comma 1. Instead, it's closing number 3 comma 4. But you see, uh, what? Let me see. But what? G of 4 is 5. Right? See that? Okay. So GeO4 is 5, 5. So 5 is not in the closing number 3 comma 4. So 3 comma 4, that function g, uh the function, the range of function g on close interval 3 comma 4 is not belong to the close interval 3 comma 4. Okay. So and then also g prime 4 is 8 of the which is greater than 1. So g does not satisfy the hypothesis is theorem 2.2 on close interval 3 comma 4 4. So it means that what? But we see that there exists, the p, fixed point, half times 3 plus square root of 13. Definitely that number is fixed point. It means that g of p equals p. But on close interval 3 comma 4, but function g on close interval 3 comma 4 does not satisfy the hypothesis in theorem 2.2. So what it said, it means that what hypothesis of the hypothesis of theorem 2.2 are sufficient to guarantee uh, uniqueness of fixed point, but are not necessary condition. Okay, so keep in mind this: the assumptions in theorem 2.2 is sufficient condition, not necessary condition. Okay, so here's the algorithm: fixed point iteration. What are you gonna do? First one, okay, now so you need to fully understand the algorithm before you write code. Okay, so keep in mind this. First one, we choose initial approximation p0. Okay, I mean, before doing that, very first thing what you have to do is to figure out whether or not that function given in problem is the what satisfy the assumptions of theorem 2.2, so that we can guarantee that what the existence and uniqueness of the fixed point. Okay, and then we gonna apply that algorithm to figure out to find out the that fixed point numerically. So choose on the approximate, choose the initial point approximate piece. Definitely, you have to choose initial approximation between the closed interval given in problem. Okay, and then generate the sequence Pn by letting Pn is equal to 0 Pn minus 1. So that's the key main the core algorithm, okay, of that fixed point iteration method. What are you gonna do? First one, give me a second. So okay, let me explain the how the fixed point iteration method algorithm works. So let's say this is graph of function g of x on closed interval, okay, AB, and then so let's say here, let's see, so here is A, right? I mean g of A, okay, and then here's A, okay, maybe A is right there, okay, and then this is a B, okay, so maybe here's this is a g of B, so g of B, okay, so now the B is maybe right here. Okay, so that G of A through G of B belong to the inner bracket, closing inner bracket AB. So and then the first one, let's say P is right there. Maybe P is right here. Okay, P is right here. There's a P. Okay, let me use other color. Excuse me. Okay, so we're gonna figure out the P, right? So starting from the initial approximation, let's say P0, starting from here, P0, there's a P0. Okay, by the way, so in this one, the coordinate at that point is what? P comma G of P. So it means that this point must pass through the what? The linear function y equals x, right? So let me plot the graph of the linear function y equals x. So y equals x must be like this. Okay, so this is graph of what? That's the graph of y equals x right here. Okay, so now what are you going to do? For the given initial, this is the initial approximation. Okay, initial approximation. So we evaluate function g at p0. Okay, so where's p0 right here? This is g of p0. Okay, now let's say this is a p1. Next what number in a sequence? Okay, next sequence. Okay, so p1. Then we're gonna evaluate g at p1. Where's the p1? So then to figure out p1, so we just figure out the point whose y coordinate. We're gonna figure out the we just the point out the point on the graph y equals x whose y coordinate is p1 right here. Since this is what that graph is, what is graph of the graph of the y equals x, it means that the x coordinate of this point is also p1, right? So p1 is right here. And then we evaluate p1, evaluate g at p1, which is this right here. This is a g of p1. Let's say we set this one as p2, and then we're going to evaluate g at p2. Where is g p2? P2 is right here. Okay, right. So here, then we evaluate g at p2, which is here. This is g of p2. This is, we set this one as p3. Then we're going to find p3 on the x-axis right here. Okay, so now you see that here, the pattern starting from p0, right? P0, and then we by evaluating the function g at p0, we're going to get p1, and then we evaluate function g at p1, and we got p2, and we got p3, p4, p5. So now the sequence is approaching the at that point p, right? That sequence approaching p, right? So this is the how the fixed point iteration method works. It's really simple. Okay, it's like the fixation method, but keep in mind is function g must satisfy the hypothesis in theorem 2.2, so we can guarantee that the existence uniqueness of uh, the the fixed point. Now we back to the lecture note. So now here so now you see that so p is the limit of g and an angles infinity, right? So this is then since gn is a g of pn minus 1, right? Because gn means pn. Pn is found by g of pn minus 1, right? And then we since g is continuous, we can put limit inside the function g. So g of limit of pn minus 1 angles infinity. This is g of p. Okay, if sequence p converts to p and g is continuous, then yeah, makes sense, right? So this technique called the fixed point iteration or functional iteration. Okay, so now then see example 3. So the equation x cubed plus 4x squared minus 10 equals 0 has a unique root in 1, 2. Okay, there are many unique roots. So this is root finding problem, right? So you can figure out you can find out the root by using this Bicester method. Anyway, there are many ways to change the equation to fixed point form. Yeah, we want to solve that problem. We want to solve this one problem using fixed point iteration technique. Then we have to change the root find problem to fixed point form, right? X equals g of x. So now, how can you find g of x? Manipulating the equation like this: x equals g1. So g1 through g5. These are the these five, functions g sub 1 through g sub 5. The satisfy this one, the fixed point form x equals g of x. Okay. First way, just from the x cubed plus 4x squared minus 10. Let's see. Give me a second. Give me a second. Excuse me. All right. So now the x minus first we define g1 as x minus x cubed minus 4x squared plus 10. Then so how can how can you find the g of x? The first way is to define function g as like this: x minus x cubed minus 4x squared plus 10. Then what? Then see x equals g of x. If a function we just use define function g, then that function must satisfy this: x minus g of x, or g of x minus x must be 0. Okay, so once we define the g as like this, and then subtracting the x from that one, okay, you see that? That should be 0, right? Let me explain the sketch papers. Okay, so now A. So here, since g of x is what? Is x cubed plus 4x squared minus 10, right? So we want to solve g of x equals 0, right? Okay, root find problems by transforming this one to fixed point form. The first A is what? We're gonna add x on both sides in the root finding problems. Okay, give me a second. Just for let me. So here we're gonna add x on both sides. Okay, so g of x plus x is equal to x, right? Okay, right. So now then we got this x what cube. Okay, x cubed plus 4x squared, and then plus x minus 10 equals x, right? Let's see. So we set this one, and then we just put a negative sign right there. It's okay. Just we just multiply by negative on both sides, right? Then we got this negative. Let's see. Let's see. Oh, yeah. Sorry about that. So we want to solve we want to figure out the g of x right here, right? So we're gonna transform this one to this. So we're gonna plug in x cubed plus 4x squared minus 10 into right here, and then move the g of x to the left hand side. Then we're gonna get this. Okay, right here. So that's the g of 1. This is g of 1 of x. Okay, and then b is the define x is equal to g2 of x. Okay, and then we define g2 of x as this: 10 over x minus 4x, and then to the 1/2. Okay, so how we got this? Because from there, the original root find problems, which is x cubed plus 4x squared minus 10 equals 0, and then we're gonna isolate x squared. Okay, so x cubed move x cubed and then negative 10 to the right hand side, and divide by 4 and take a square root to isolate, and then to get x equals something. So the 4x squared is equal to see there. Let's see the first one. Yeah, so give me a second. Oh, sorry about that. So the first one, that was a C. The B, we just divide by x first. Okay, then we got x squared plus 4x and then minus 10 over x equals 0 over x. But 0 over x is 0, right? Okay, and then we move the 4x minus 10 over x to the right hand side. Then x squared is equal to 10 over x minus 4x. And then we take a square root. Then x is equal to the square root, right, which is 10 over x minus 4x to the 1/2. But we got plus minus sign, but we dropped the negative sign because we know that the the x must be between. You see that here, the x is in should be in the closing the row 1, 2. It must be positive, right? So we drop the negative sign. So we got this. And then C, this is what I said here. We gonna given that x let's see, x cubed plus 4x squared minus 10 equals 0 from the root finding problems. We're gonna see, we're gonna let's see, we're gonna move the x cubed and negative 10 to the right hand side and divide by 4 and take a square root. So x squared is equal to 10 minus 1/4 times 10 minus x cubed. Then x is equal to, or so we drop the negative sign, okay? So 1/2 times 10 minus x cubed to 1/2. Okay, C. And then D, okay, let's see, let's see. In D, first, let me write down x cubed plus 4x squared minus 10 equals 0. First one, we're gonna, to take out x squared from the first and second terms. So we're gonna x squared and then x plus 4 minus 10. Okay. And then so from there, and then we x squared and then 10 minus x plus 4 minus 10 equals 0, and then we move 10 and then divide by x plus 4. Then we get this x squared is equal to 10 over x plus 4. Then x is equal to square root of x plus 4, right? Okay. So the E. So the last one, E, is what? X minus x is equal to g5 of x, and then g5 of x is defined by this x minus x cubed plus 4x squared minus 10 over 3x squared plus 8x. So where that comes from? What is this? Take a look at the fractions. Okay. So now then, this is equal to x minus top one is nothing but a g of x, right? Okay. So see. Okay, minus this should be f of x, right? So this should be f of x. Okay, we want to express f of x as x minus g of x, right? Sorry. Okay, x minus g of x. Okay, like this. So top one is actually f of x, and the bottom one is derivative of f prime, derivative of f of x. Where that comes from? We're gonna talk about this one later. This is a really important topic. Okay, so now let's see result. So apply the fixed point iteration technique. It turns out that this one G1 is the diverge, and G2 undefined, G of 3 30 iterations, G4 15 iterations, G5 4 iterations. We see that here the last one, the one is best the performance. This one show best performance, right? So the purpose of the fixed point iteration is to illustrate the following question. How can you find the fixed point problem that produces a sequence that reliably and rapidly converts to a solution to a given root finding problems? You see there are, in this example, there are 5 choices. And then do we have to, find the all possible way to define g of x and then run the and then run the these problems, try for each, and then figure out which one is best. Is I don't think that that's the efficient way, right? So we need to figure out what's the way to define function g of x so that we're gonna get the best performance. So that's the question, right? So here, first one, we'll see theorem 2.3. To figure out that one, we need to see fixed point theorems. So well, I'm going to cover theorem 2.3 next time, okay? So let me stop here. So I'll cover from the theorem 2.3.